Hello everyone. Today I will represent our team to present VivaHead due to Professor Abhijeet and Dr. Yiming's schedule conflict. Our work is mainly about generation-augmented Gaussian avatars for single-image full-head reconstruction and animation. Given one portrait image, we aim to reconstruct a vivid animated full-head avatar, including side and back head regions and expression-dependent details. Let me first introduce the task. Our task is single-image full-head avatar reconstruction and animation. Given single image, we want to reconstruct 3D head avatar that preserves identity, covers the complete head, including hair and back, and remains faithful under new poses and expressions. We also want a feed-forward inference that reconstructs the avatar in minutes. So the goal is to combine three properties: full head geometry, controllable animation, and feed-forward inference without per-subject optimization. Current single-image animatable avatars methods, such as Portrait 4D and GP avatars, show that a single portrait can support convincing facial motion. However, many methods mainly reconstruct the visible face, while the side and back head geometry remains limited. Moreover, input contains only one observed expression. Wrinkles under different expressions are under constraint, and that limits the vividness of the animated avatar. Current full head reconstruction methods aim at reconstructing a full head structure. Methods such as panel head, sphere head, and ID sculpt have successfully recovered side views and back head regions. However, the reconstruction quality is still limited in back head regions, especially for complex hairstyles. More importantly, these reconstructed heads cannot be animated with new expressions and poses due to their reconstruction-only design. Overall, existing methods usually meet only part of the function because they emphasize only one or two functions listed in this table. Some methods only provide frontal animation and some only reconstruct static full head. Here we propose VivaHead, which aims to realize full head reconstruction and animation from single input portrait. Our VivaHead first synthesizes complementary views that is essential for full head reconstruction and animation. Multi-view generation provides side and back head information. Multi-expression generation provides facial variation. Then a feed-forward canonical Gaussian avatar is predicted, and a lightweight refinement improves geometry, hair, and facial details. This page is our pipeline. Given a single image, we generate multi-view and multi-expression observations. All the observations, that is, the generated images, are encoded and fused by reconstruction branch. The output is an initial full-head Gaussian avatar in frame canonical space. Refinement is then optimized this canonical Gaussian with the generated observation, adding sharper geometry and details. The two augmentation branches are designed to realize two functions, that is, animation and full-head reconstruction. Multi-view augmentation generates 6 fixed views around the head, directly targeting side and back head reconstruction. Multi-expression augmentation reenacts the same identity fine-tuned on VFHQ. The sampled frame targets appearance changes absent from a single static expression. All observations are fused into one canonical Gaussian avatar. A shared Dino V2 encoder extracts image features. Canonical queries aggregates information through self-attention and cross-attention. An MLP predicts Gaussian attributes in frame canonical space. Expression-neutral training reduces source expression leakage. Minute-level refinement sharpens details that the feed-forward pass may not fully cover. Our rendering scheme follows LAM. The reconstructed avatar is a frame-based canonical 3D Gaussian representation, animated with linear blend skinning and rendered by standard 3D Gaussian splatting vectorization. Here we show whether the reconstructed representation behaves as intended. On the left is the forehead reconstruction result, and on the right is the animation result. For animation, we compare our method with GAG avatar, LAM, fast avatar, portrait 4D V2, and GP avatar. VivaHead achieves strongest quantitative result across PSNR, SSIM, LPIPS, and identity similarity. As shown in the figure, we reconstructed avatar not only follows the driving motion faithfully, but also exhibit more realistic expression-dependent detail changes during reenactment, leading to substantially more vivid results than LAM and fast avatar, especially for expressions that should trigger visible local facial detail variation. So on this side is the qualitative result. And this slide shows the video comparison against different animation methods. Here we show 3 reconstructed identity rendered from multiple viewpoints while they animate. As shown in the video, our method achieves faithful animation across different viewpoints. For full head reconstruction, we compare with full head reconstruction method and animatable avatar baselines. Frontal-focused animation methods usually do not target backhead reconstruction. Full head methods model the backhead region, but they still show blur, artifact, or incorrect hairstyles. VivaHead produces more coherent and reliable side and backhead regions while remaining animatable. And here we show additional full head reconstruction results. The quantitative results support the visual comparison. VivaHead achieves the strongest overall performance across the compared baselines. They support the full head reconstruction part of our method. The ablation study connects each component to the main claim. Without multi-view augmentation, it results in poor full head geometry. Without multi-expression augmentation, animation becomes less vivid, and without refinement, the final result loses sharpness and details. So the ablation matches the design. That is, each module matters a lot. Here we also generalize the model to diverse inputs, including out-of-domain data, cartoons, anime-style images, and paintings. Canonical Gaussian avatar supports animation, relighting, and editing. Since each covers full head, this application remains more consistent across frontal, side, and back views. Frankly speaking, VivaHead also has many limitations. Highly usual backhead geometry and complex hairstyles remains difficult from a single image. Some information is still ambiguous even after generation. Future work could focus on better handling on modeling complex hairstyles, particularly fine-grained hair structures, and also challenging occluded cases. To conclude, we propose full head reconstruction and animation pipeline from single image. By generating multi-view and multi-expression observations, it provides richer information for feed-forward canonical Gaussian reconstruction. And with a lightweight refinement stage, VivaHead enables more faithful, high-fidelity animation while improving full head completeness and identity preservation. Thank you all, and I really appreciate your time.
Thank you for the presentation. Are there any questions?
Thanks for the presentation. I see you have comparison with other methods, and your result is superior than others, except the CSIM, if I remember correctly. Do you know why? What it means? Yes, this one. Why the unique 3D is better in this CSIM? Because the others, you're way better, right, than the other methods.
Yes. I believe unique 3D is not really it's more of a object reconstruction method. I'm not quite sure about this one, really. Maybe we can discuss this one later.
Okay, no problem.
Yeah.
So another small question.
Yeah.
I mentioned, I saw that you show limitations. I understand, like when the back hair is complicated, it's difficult to reconstruct. But it's because you still reconstruct from one input image.
Yes.
So if the image has a very unusual expression, will be that also an issue?
No, because we also have this. Just a second. We also have this expression neutral training stage, which it explicitly removes the expression from the source image, and that will keep the input image for the canonical reconstruction to be expression neutral,
okay.
And therefore, yeah, the very unusual expressions will not be a problem for our pipeline.
Okay, thank you.
Are there any other questions? Otherwise, I can ask one also. You're solving a very difficult problem here, right? Like kind of going from a single image to a fully animatable 3D full head avatar. Did you investigate flavors of this method that take additional images or additional conditioning signal? Like, let's say, a video of a person or 2 or 3 images. Like, is it easy to extend to take additional inputs? Because then the problem is more constrained, right, and becomes easier.
Yes, so the setting of our problem is really just for single image, but if you really want to put additional inputs into the model, then maybe you can just remove the multi-view or multi-expression models and then just put your real additional models in it. But and then we can also make sure the rest of the pipeline works with real inputs, and that would, I think that would actually end up with better results because you're inputting real images. But the key point of our design is that we can also achieve similar results even from just one image.
Okay. Any other questions? Otherwise, I'll ask one more. You mentioned motion models as future work to expand the kind of dynamics of the animation. Like, do you have any thoughts on how you would approach this? For example, to model the motion of long hair strands?
You mean the future works?
Like at the very end, you mentioned the motion or animation as one of the limitations, I think. Yeah, richer motion models for more expressive animation.
Yeah, so because we use the linear blend skinning for animation, right? So the hair or like animation that are not modeled by frame cannot be expressed. So I believe maybe we can do some extensions on the animation side of the pipeline so that maybe very difficult expressions or hair motion can be modeled as well. Since currently we use frame animation, so hair is not included.
Mm-hmm.
Yeah.
All right, thanks. If there are no more questions, let's thank all the speakers again and conclude the session.